We started our angled launches and we kept them ground to ground. Or what does that mean? It means we ended at the same vertical position as we started, right? Or delta y equaled 0. And we got to see some different kind of cool solutions with delta y equals 0, okay? Well, symmetry, it's still there, but now we're going to add on to it. And so down below, hold on, we've got a cannonball that's going to be launched from a cannon with a velocity of 95 meters per second at an angle of 63 degrees above the horizontal from the point on a cliff that's 65 meters above a level plain below. Did you follow that? What do you see? Hopefully you see a cliff. Where's the cannonball going to start? On top of the cliff. So I'm going to start drawing our picture here. And now I don't care about the cannon. It's not a projectile and we're not looking at forces yet. And so really I'm just caring about the cannonball. What are we going to do with the cannonball? We're going to launch it horizontally. Not today. We're going to launch it at an angle. And so this initial velocity, which they do tell us is 95 meters per second, it's at an angle with the horizontal. Now, 90% of the time, not 100, 90% of the time, our angles are going to be with a horizontal surface. Because if you think about almost any sport, where's the ball? We reference the ground. We kick the soccer ball, the football, whatever, from the ground. Golf ball is hit from the ground, right? And so most of our angles are with the horizontal, okay? I don't want to say assume it, because as soon as we start, oh, it's always horizontal. Here comes somebody that throws a ball against the wall, which is a vertical surface, and we have to transition with an angle with the vertical, okay? Or do y'all remember the game tetherball? Tetherball is with a vertical pole. And so we'll do tetherball later with rotation, but most of your angled launches are going to be launched from a horizontal. And so this 63 degrees is going to be from that horizontal. Good? And they tell us the cliff is 65 meters, basically tall, right? And so I'm going to go with standard sign convention. I'm going to call the ground 0 meters, and the cliff is 65 meters. Now that's vertical, so let's think vertically. The ball is starting at 65, so I'm going to say y initial equals 65. Now eventually it's going to end on the ground, okay? And then what are we going to solve for? How long is the ball in the air? We're solving for time. And time is dependent on which axis. What should your plan A be when solving for time? Horizontal or vertical? The vertical. So we'll start out trying to find time in the vertical. By the way, that's just plan A. You can still calculate time with horizontal, but your plan A, I would always go for the vertical. How far from the base of the cliff will the ball land? What are we solving for there? How far from a horizontal distance, right? AKA, what's our vocab word? Range. And then C, D, and E all kind of interrelate. C says, what's the vertical speed as it lands, or vertical velocity? And so vertical final. D, what's the horizontal when it lands? So V final X. E, what's the velocity? No mention of direction. And so this is when it lands. This is that impact velocity. And hopefully you remember that it's going to land at some angle. And so why have C and D? Well, if you know the horizontal and vertical components, can't we solve for the hypotenuse? E is going to be our hypotenuse. And then the last thing to solve for, not necessarily the last ever, but the last on this problem, how high above the top of the cannon will the ball reach? It's kind of a max height question, but they don't want the height above the ground. They want the height above the cliff, okay? And I'll show you later. This is just going to be the vertical upwards displacement. Everybody good with what we're solving for? Okay, let's go back to the picture. Let's draw that projectile trajectory, okay? And so we launch it northeast, I have in my picture. And so don't pick up at the end of the arrow. Remember that initial velocity vector should be tangent to the parabolic path, right? And so we start back at the ball. Maybe it goes up a little, maybe it's a lot. I'm not necessarily drawing this to scale. And then it comes back down. Now I hit pause there. Notice where I paused my red trajectory. Why did I pause it there? Right. That's where we return to that 65-meter vertical position, right? Do you see some symmetry? So the top part has some symmetry. Don't forget your symmetry. So just to kind of recap some of that symmetry, at this moment, what is the velocity? And I know I drew it underneath because really your ball is like right here, okay? What is the speed of the ball at this point? 95, right? So previously we said the launch speed equaled the impact speed, but that was only if it was symmetrical. So we're not impacting here, but that instantaneous midair velocity is 95, right? And you could break it up into components and such. We know that this angle is also 63. Now let's keep our red path going. Well, fast forward, unpause, what's going to happen the rest of the way? It's going to keep going down, right? I don't want to get too vertical. It shouldn't land exactly vertical. I'll put a little tilt to it. But it's going to land. Here I have it above the ground. I mean, you'll see some pictures draw it below. That's fine. But it's going to hit at an angle. Compare this angle to the 63. Is it going to be equal, less than, greater than 63? Concepts here. Why greater? Why would it be greater? In which direction? In the vertical, right? So vertically, it's speeding up that much more. And so we have a V final Y that's going to be bigger than it was. Gravity speeds this ball up as it keeps falling down. Horizontally, it should be the same, whatever we had. I haven't found these components yet, but it's increasing its vertical velocity. So if a component is bigger, when you Pythagorean theorem, right? Oh, that's the hypotenuse. Sorry, that's the next question. Compare your impact speed. Is it 95? It should be greater, okay? Same reason, you have a component that's bigger, right? And so your impact speed should be bigger than 95. And so we're hitting on some concepts. What if they had you rank several positions? Positions A at the beginning, B at the peak, C, that symmetrical midair, and then D at impact. You can hopefully rank the speeds and the angles, right? Okay. And so now, notice start to finish, it's not symmetrical. And so whether you want to embrace symmetry, it would be one chunk of the problem. You have that rest of the way down. And so normally, unless I'm told otherwise, I like to look at start to finish, right? It's launched from the cliff, it lands on the ground. But like in the last problem, they talk about the peak. So I'm not going to look at big start to finish there. All right. I highly recommend at the beginning, the first thing you do with angled launches, whether it's ground to ground or not, is find your components. And so Vx and Viy. Now, last class, we used SOHCAHTOA to find these, and double check your calculator. It should be in what mode? Degrees. Last time we said we'll use cosine for the x component, and I said I started from scratch. We solved for the component, and we said it's equal to Vi times cosine theta. I haven't plugged in numbers yet, but I think this is just above. This equation, again, is what we'll use 90% of the time. As long as that angle is touching the horizontal, you can use this equation to find the horizontal component. What about for the vertical? Well, it's opposite. We're usually given the hypotenuse, and so it'd be the hypotenuse initial velocity times sine theta. And that's another one. Now, I don't like telling you to memorize. My hope is that we practice this so much, it goes into like your muscle memory, right? Or if you don't memorize it, on the formula chart is sine, cosine, tan. You just draw your triangle, figure out who's what part, opposite, adjacent, hypotenuse, and you start with that, okay? Just like we did last time. If you love memorizing though, I would memorize these. They're very, very 90% of the time true. So now let's plug in some numbers. So Vx is going to be 95 meters per second, cosine 63. Again, got to be in degree mode. Punch it in. Let me know what you get. What do we get? What'd you get? Okay, so 43.1 meters per second, since our velocity was meters per second. And so that's the horizontal component. Vertical component, I'll do it right here. We'd have 95 times sine 63. Let me know what you get. Okay, we'll just round it to 6.5. Okay, and that would be meters per second as well. And so these are the horizontal and vertical velocity components that we're going to use in our kinematic equations. We are done with 95. Done, done, done. We're not doing anything else with 95 unless they ask us about returning to that same elevation, or if we're doing some kind of comparison, we impact greater than 95. But we are not going to plug 95 into our kinematic equations. Good deal? That's why you have all the little X's on those equations. Imagine they're Y's, right? And so you can't put hypotenuses in those equations, just the vector components. All right, so now that that's out of the way, and I highly recommend making that your step 2 after your picture, right? Because chances are you're going to need both. Part 1 says, how long is the ball in the air? We said earlier, let's do that vertical. So what do we know vertically? Well, we just found Viy, and we had what, 84.65. What else do we know vertically? And I'm going to go start to finish. That's usually my plan A. Right? Acceleration in the vertical is that negative 9.8. If we go standard sign convention, which we are, I'm going to go on and use 10. Which one do you use on our exams? You can use 10. Okay, we don't do both and try to play games on multiple choice. Free response, you're going to show all your work. So I know what you're doing, right? Hint, hint, show your work. Okay. What else do we know vertically? The cliff is not our projectile, but the projectile starts on top of the cliff and goes to the ground. So we can either put it in terms of positions or we can put it in terms of displacement. So let's do both. Initial vertical position is 65 meters. Final vertical position, the ground, we said is 0. And so what is your vertical displacement? Remember, it's final minus initial. Negative 65. When you do standard sign convention, for objects that fall down, they have a negative displacement. All right. So usually when you get 3-ish numbers, start seeing, can I solve for time? And so look at your equations. Which one are we going to use to solve for time? Notice what we don't know. What variable isn't mentioned at all? We know initial velocity, but we don't know final. So which equation doesn't need final? The second one. And so we come, I'm going to slide to the left. And so delta y, I can put it, I already figured out what displacement is, equals VIYT plus 1/2 AT squared. Go to plug it all in. Negative 65 equals a positive 84.65. We're looking for time. Plus half of negative 10. If you go ahead and put negative 5 there, that's okay. Times t squared. And so how are we going to solve for time? Is this like last class where I can say, oh, divide the whole thing by t? One set of t's cancels out. Is that true on this one? That was true when we looked at the symmetrical problems and delta y equaled 0, right? But delta y does not equal 0, so we cannot reduce the time. And so now what's running through your head? Quadratic. Okay, now there's mixed emotions maybe about quadratic. Maybe you learned a song, maybe you know how to do it in the calculator. I personally never was taught a song, and I've went 20 plus years in physics without knowing the quadratic equation. So how in the world are we going to do this? By the way, if you love quadratic, ABC, you got to add 60, you got to make it equal 0. So I'll identify the pieces. I just don't know the song. Or you can graph it. I grew up before graphing calculators were a thing. And so if you want to do quadratic, sing your song, put it in the calculator, go for it. How have I went 20 plus years without it? Find that final velocity that we don't know first, third equation, and then use the first equation. Ms. Earhart, you're using 2 equations. Isn't that double the work? Well, at least those 2 equations are on the formula chart. I could send you on a scavenger hunt to look for the quadratic on that formula chart, and you'll never find it. AP doesn't give it to you. And true story, on the AP exam, you don't need the quadratic. If you know it and want to save maybe an equation, do it. So whoever loves quadratic, start going to town, okay? let's do the workaround, and I'm running out of room. So this is still sum of part A. We're still looking for time. Okay. So if you don't use quadratic, step 1, solve for that final vertical velocity with the third equation. And then later we'll use the first equation, okay, to find time. And so final vertical velocity is what we're solving for. I'm just going to keep it squared for right now. The initial was that component 84.65 squared plus 2 times negative 10. And then our displacement is negative. So negative times negative, it'll go away, right? And so grab the calculator. Do your 2a delta y, should come out a positive number. Add to it the 84 number squared, and then square root that sum. And tell me what you get for the final vertical velocity after the square root. So grab that calculator, start punching in. I don't have this number memorized. And let me know what you get. I think 4 people are calculating. Wait, did you do quadratic? Okay, I don't want time. I was right here getting my final vertical velocity. Sorry. I'll ask for quadratic here in just a second. We'll compare answers. So what's this final vertical velocity? 92 meters per second. Sounds familiar, okay? But wait, there's more. Remember how I told you a week or so ago with this equation? When you square root, technically your answer can be positive or negative. Now time is never negative, right? But here our velocity, well, it makes sense. It could be positive, it could be negative. So the calculator gives you a positive, but no more physics than your calculator. When this thing hits the ground, it's moving what vertical direction? Down. How do we represent that here? It's got to be a negative. And you're like, what's the big deal? It's actually in the next equation. It makes a big difference. So remember our 2-step workaround. Step 1, find the final vertical velocity, third equation. Step 2, and I'm sorry I'm bleeding over, okay? Step 2 is to find time with the first equation. And so if we spend a little time, again, do this sometimes. I don't do it every time either. But let's solve for time before we plug in numbers, okay? I got to subtract the initial velocity from both sides. And then I got to divide both sides by that acceleration. And so now I'm going to plug in my numbers. Now we know the final velocity. Now work with me here. What if I didn't realize it was negative? I put in a 92, calculator spit out 92. That's what I'm going to go with. Minus our initial, which was 84.65, divided by -10. Now notice we're going to subtract and get what? 7/8-ish divided by a -10. Wait, that would be a negative time. Well, let me just erase the negative, right? No, here you get a different number. And so this is why it's super duper important to recognize that sign, okay? It doesn't just make a sign difference, it makes a numerical difference here. Now, rather than subtracting those two numbers, we're summing the two negatives. And when you divide by a negative acceleration, we get a positive time, as we should. And so now, calculate the time, not with quadratic, just keep holding that. What time do we get with the first equation? (17.6 seconds. All right, quadratic people, what'd you get? Yeah, so 17.7 with quadratic, that's fine. So we had done some rounding along the way. And by the way, if you use 9.8 and I use 10, little bit different, but it's the spirit of same time, right? And don't lose sleep over a decimal, over a couple pennies, right? Show your work, you'll be okay, all right? Now with quadratic, it can spit out a negative time, right? But we don't want to use the negative time portion, okay? Questions on number 1 or A, whatever. So this is our answer for A. So no, you don't have to do quadratic. All right, that one does take the longest. The rest will go pretty quick. What about B? How far from the base? So horizontal distance, range. We use the same equation 99.9% of the time. What equation do we use in the horizontal? Not the first one. Because in the horizontal, what's true? What something equals 0. What equals 0 in the horizontal? I think I heard it. Acceleration in the horizontal equals 0. So if you did go to use the first one or the third one, when you zero out AT, all you're left with is initial velocity equals final velocity. And hopefully at some point you're like, oh yeah, constant velocity in the horizontal. And so we can use the second equation in the horizontal. And I'm going to show it this one last time. Okay, at some point, hopefully you catch on, muscle memory, right? That 1/2 AT squared in the horizontal direction is going to zero out. So it's really just delta x equals horizontal velocity times time. Or rearrange it, it's our defining equation for velocity. And so, good thing we already found that horizontal component. We got 43.1 meters per second. And then time, well, we care about when it lands, not time to peak, not to the time till it returns to the same initial vertical position. It's till it lands. So we're going to use that whole time, 17.6. And what do we get here? Multiply it out. So pick up that calculator, somebody, multiple people. (43.1 times 17.6 is, say it one more time. Okay, 758.56. So you can probably just round that one to either 759 or keep that 0.6 if you want. Okay. And so that's a long range. That's like 6 or 7 football fields. That's okay. That's okay. We can have these extreme things in physics land, right? It's a cannon. All right, C. What will be the ball's vertical speed as it lands? Hey, didn't we already find that? So sometimes the two-step workaround to quadratic gets future answers. So we had already solved for that. we know the final velocity is a negative 92 meters per second. Now, technically, they said speed, so we can just give 92. Okay. If you put negative 92 on that one, that's okay. And then the horizontal, what do we know about horizontal velocity? Concept. Constant. And so there's your concept. We know it's constant. And so initial equals final, that was the 43.1 meters per second. Now, why is it saying speed and speed? So C and D are building us up to part E. E says, what will be the ball's velocity as it lands? So again, I'm just going to kind of zoom in or redraw that impact velocity. So when it hits the ground, it still has components, right? So that final vertical velocity, yeah, it's negative 92, or it's positive, it's okay. Pythagorean, the negative is going to go away. And then the horizontal, 43.1. And so to solve for the hypotenuse, we would get what? Or do what, sorry. Right triangle, looking for the hypotenuse. Pythagorean theorem. And so that negative 92 is going to square. The negative is going to go away. Y'all, I don't even punch it into the calculator, okay? Because you don't want to accidentally minus, right? And so I don't even, when I realize, hey, that's going to go away, I just say 9(2) squared plus the 43.1 squared equals whatever my answer is, and it's squared, so give me the answer after you square root, okay? And so while you calculate, a reminder, what we did conceptually to start, we had said, well, it's going to travel more downward than upward, and so it should be greater than the launch speed. We should get an answer greater than 95, okay? So square, square, add, square root. Let me know what you get. 10 what? Okay, so it rounds to like 102. And so 102 meters per second. And that is greater than 95. So yay. Now they don't tell us to, but we could find the angle that it hits the ground, right? We know the launch angle is 63. Let's add 2. How do we find the angle that it hits the ground? We can use vertical speed and not time. Angles, you got to do SOHCAHTOA. And the nice part about knowing all sides of the triangle, you can pick your favorite. Textbooks use tan, but if you want to use sine and the hypotenuse that you just calculated, go for it, right? And so let's do sine. Sine theta is that opposite over hypotenuse. Now to solve for theta, remember we got an inverse or arc sine. And so theta is equal to inverse sine. And then my opposite. Now, negative 92, it's okay. I think you don't even need that. We know where the angle is. I don't think it doesn't get confused like tan. Okay, with tan, I always absolute value. And then hypotenuse, we found to be 102. So let me know what you get. And reminder, if you get a number less than 1 or you get point something, my first question is, are you in degree mode? Because usually radian gives you a decimal, like less than 1 value. And you're like, that's the angle? No, it's not. Switch to degree mode and you should get a more reasonable angle. So what'd y'all get? 64 degrees. And it would be above the horizontal. That's the angle it makes with the ground. Okay? So even though they didn't ask us today on this question, that's a common question. What's the impact angle? Okay? All right, last one here. So we've been looking at start to finish, but sometimes they just want to know something about the peak, right? How high above the top of the cannon will the ball reach? So this is only caring about going to the peak. So we already said that's going to be a vertical displacement only for the upward direction. And so if you want to kind of redraw that little bit, that's all we care about. Pause the video. That's all we care about. And so from initial launch to the peak, what do we know? Well, acceleration is still -10, right? Ball's moving up. Gravity always pulls down. What else do we know? Vertically, right? Initial vertical velocity is that same one we found above. And I think that was the 84.65. What about final velocity at the peak? 0, right? Remember, gravity doesn't quit, but it's that momentary stop in the vertical. It's still moving horizontal, but here we're just using vertical information. And we're looking for that delta y. Now, true story, I could say initial vertical position is 65 and solve for the max height, but that would all be relative to the ground. You'd have to subtract out that 65 to get your final answer. I'm just taking a displacement approach. Notice I do not know the time up. Sure, I could go find it. Or what equation can we use without time? The third one. And you're like, oh no, not that one again. It's okay. Don't worry about the square root business because we're solving for delta y. So again, every once in a while, solve for your unknown before you plug numbers in. We can subtract the vertical initial squared, but don't square that minus, right? And then divide by 2a. And this should be our vertical displacement. We should get a positive displacement, right? We're going upwards. So we should get a positive displacement. And so let's plug it in. 0 minus 84.65 squared, but don't square the minus, divided by 2 times -10. And so there, hopefully you see why you don't square the minus. The minus should end up canceling the negative of our gravity. So let me know what you get here. And I think it's a big number, if I remember correctly. Let me know what you get. 1,000? I don't remember that big. 358 sounds familiar. So I don't know what you could have done to get 1,000. It sounds like you squared. Yeah. Okay. So try it again. Hopefully it works itself out. But yeah, this is why we should be calculating daily, right? We got to figure out those finger slips ahead of time. Questions on a non-symmetrical angled launch. There's still symmetry, but there's more to it. All right. Next one, Number 12. How about y'all try the tennis ball one, but hold on, I'm gonna get you started, give you a little bit of guidance, and then y'all are gonna spend 5, 8, 10 max minutes trying that, and then we'll do Tiger Woods, hence the Tiger Woods motivational quote at the beginning. Okay. So on the next page, page 12, it says a tennis ball is accidentally whacked at a backboard from ground level. So, you know, maybe the tennis ball gets hit and you're hitting it in the lower region, right, close to the ground, with a speed of 35 meters per second and an angle of 60 degrees. The backboard is 7 meters high. It's placed 5 meters away. Does the ball make it over the backboard? Now, I don't know if you caught the way I read the problem. Someone pointed out last period. It says a tennis ball is whacked over a backboard. So the answer is yes, moving on. That's not the spirit of a physics question, okay? So maybe we're aiming at a backboard. Let's find out, does it go over? So it is a yes or no question. Do you think you're gonna get AP points for a yes or no question? No, what are the points for? The physics leading up to that yes or no, okay? And so really to answer this question about does it hit the backboard or does it go over, what do we need to solve for about the ball to answer this? Because it doesn't directly tell us what to solve for. Okay, so peak or vertical position, right? We don't really know if it's at peak or if it's on the way up, on the way down, right? But we need to know that vertical position, we got to solve for it. And they told us the backboard is 7 meters high. And so I'll get you started with a little picture. And so the ball, we'll say, is basically starting on the ground. We're going to hit it up at 35 meters per second at a 60 degrees with the horizontal. So maybe give ourselves a level playing ground. Maybe the backboard is over here. We know it's 7 meters tall. So our ball can do one of two things. Does it go up, 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 and go over? Or does it go up, 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 and hit the backboard? And so those are the two possible pathways, not drawn to scale, that it could follow. And so in order to answer the question, you need to know, well, where is the ball when it makes it that horizontal distance away, which, by the way, they tell you it's 5 meters from the backboard, okay? And then once you know the yes or no, again, you can't answer it unless you know that final vertical position. If yes, it does pass over, then how far above the backboard does it pass? And if not, how much below the top? So you're comparing it to the 7 meters, okay? All right, I'll give you 5, 8-ish minutes to work this one out, and then we'll Tiger Woods. All right, so let me, okay, so in order to solve for does it hit the backboard, we said we need that final vertical position. Now, don't assume that it's at the peak whenever it reaches that backboard, okay? But we need to find time first. And they gave you enough horizontal information to find time. Remember the equation we use every single time in the horizontal is that second one, but now I'm going to leave off the 1/2 AT squared because hopefully at this point we know that horizontal acceleration is 0. And so they did tell us it was 5 meters from the backboard. So that horizontal distance traveled is 5 meters. Now the horizontal velocity, we don't know yet. No, it's not 35. We got to find that component. And so if I kind of redraw and zoom in, we've got 60 degrees. We're looking for the x component. And remember, you can take the hypotenuse, 35, times cosine 60. What'd y'all get for that? 17.5, and it would still be meters per second. And so we know 17.5 meters per second, and then times time. And so to solve for time, 5 over 17.5, what time do we get? 0.28. Is there one more digit? Only because this isn't a final answer, so I like to keep as many decimals in 3, 4, 5. Okay, so 285 seconds. Good on time? So now, to get that final vertical position, we do not know the final velocity. True story, we could go find it, but we don't need to if we use the second equation. And so you may be thinking, oh, but you said that's quadratic. It's only quadratic if you're solving for time. Now we know the time, we're solving for that final position, okay? And notice I left it in terms of position. Okay, you got to be ready for both type. Initially, we said it's going to start on the ground, so that would zero out. And the initial vertical velocity, oh, I haven't found that yet. So to find the vertical component of 35, we would do the sine, or you could Pythagorean with the two sides you know. And so VIY would be that 35 times sine 60. And what do we get for the vertical component? 31? Oh, 30.31. And it's still meters per second. And so we can plug that in for our initial velocity. And then using the time that we previously found, plus 1/2, I'm going to keep with -10. And then time again, don't forget to square that last one. And as you calculate it out, or maybe you already have, this is going to be the vertical height, the vertical position when it makes 5 meters across, when it gets to the plane, to the backboard's plane, right? And so what's the final vertical position? What do we get? 8 point what? 23? So 8.23 meters is where it is. And if we look at the picture, maybe that's the blue path, right? So 8.23 meters, does it hit, the question says, does it make it over the backboard? The answer is yes, and we have the work to show it. If your answer is yes, how far above the backboard does it pass? So we just subtract out the 7. And so 8.23 minus the 7, it passes 1.23 meters over the backboard. Good deal. So anytime there's a yes or no, which by the way, those are rare. Those are rare. We typically don't have, true, false, or yes, no. There are multiple choice type, but it's about the justification, the work leading up to that answer. Okay, I got less than 10 minutes. Let's do Tiger Woods. In case you didn't know, he's a golfer. He's going to hit a golf ball at a speed V from an angle of theta above the horizontal. The ball lands in the hole at the same elevation. What did I just hear? I heard this is symmetrical. Same elevation, yay, symmetry, at which it was hit. State your answers from A to C in terms of V, theta, and G. Wait, did we hear any numbers? This is not students' favorite at this point, but this is what you'll definitely see on the AP exam. Some multiple choice questions will be variable based. At least one free response is variable based. And let me just show you a little bit in the packet. Page 18 in OneNote, I titled AP Free Response 2021. Look at that. It's not a projectile the whole time, but when the motorcycle passes over the cars, look at that symmetrical parabolic pathway. This was a projectile problem. And notice there were no numbers. This was a variable solve, okay? So that may not be a projectile variable solve on this next year's exam, but expect some kind of variable solve. And so don't worry, we'll do these all throughout the year. Hopefully by May, you feel better with them, okay? So symmetrical, draw out a picture real quick. Golf ball, up, 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 and down, right? Initial velocity, V, angle is theta. Now, if it's symmetrical, we know some things, right? And so at the peak, what do we know? What's true at the peak? Velocity in what direction is 0? Vertical. So Vy at the peak is 0, but isn't it still moving in the horizontal? It'll be smaller than V because it's equal to the horizontal component. And then when it hits the ground, or the split second before, we see that symmetry, right? And so the split second it hits the ground, you know, whether you draw it towards, you'll see pictures either way, but that impact speed will equal your launch speed. The angle equals the launch angle. So that symmetry gives us a lot of nice things, okay? All right, so first thing we're solving for, how long does it take for the ball to reach the highest point? Do I need to consider ground to ground? No, it's from the hit at the ground to the peak. So what do we know? In time, we typically use vertical. And so that's what we're looking for, time. We know acceleration is, don't even plug in 10. Variable problems, keep the constant. Now I do want to appreciate sign convention. And so I'm going to go with up is positive. So I'll make gravity negative. What else do we know? Ground to peak. And would that be the initial or final? It'll be the final if we pause at the peak. And so the final at the peak and the vertical, 0. What about initial? Vertical. It's not V, because that's at an angle. You can't put a hypotenuse with my vertical information. There we go. And so we want to use the vertical component, which is opposite. And so it's hypotenuse V times sine theta. So how do we find the time? This is just the time up. Notice I don't know distance, so I'm going to use the first equation. And so V final Y equals V initial Y plus AY times time. To solve it for time, it'd be final minus initial velocity over acceleration. Plug in what we know, 0 minus V sine theta over negative G. If you didn't put in negative G, if you didn't appreciate sign convention, you'll end up with a negative time, and that's just never good, right? And so here it would reduce to just V sine theta over G. Now, a reminder, it said state your answer in terms of V, theta, and G. Not that you have to have them all, but your answer can't have like H or X or Y or even A. And so our answer has sine. That's a trig function. That's okay. It's not a physics variable. So we've played their game. This is the time to the peak. Everybody good? Next, what time, what's the total time that the ball is in the air? Well, thank goodness it's symmetrical, ground to ground. We can take that up time and do what? Multiply by 2. So if time up equals time down, then I can take the time that I found times 2. And so it would turn into 2 times v sine theta over g. That's the total time. Once again, the only physics variables are v, theta, and g. 2 is a factor, that's okay. Sine is a function, that's okay. Next to last, how far away is the hole, aka the range? So I'm gonna do this one quick. We got horizontal velocity times a total time. We want it to hit the ground for total range, right? So we'll use our answer from above. Horizontal velocity would be v cosine theta times 2v sine theta over g. Now, although I could leave it right there, typically they want you to, finish the physics, finish as much of the algebra as you can. What's v times v? V squared. So you could end with 2 times v squared cosine theta times sine theta, which, by the way, I don't remember the math trig identities. I think cosine times sine theta equals something else, but they don't expect you to take it that far. So this is your final answer for the range. This is what's called the range equation, by the way. Range equation, okay? But it's only good ground to ground. It's not good if you have a cliff problem, okay? What if we were on a different planet where gravity was half? How would that change our time and range? So we would hit at the same v and theta, but if I have a smaller gravity, notice in both questions, gravity's in the denominator. What kind of time and what kind of range would that produce? Greater. It'd be a twice factor, right? If gravity is half, you would have a greater total time and a greater range. And so a lot of times variable problems are helpful for playing the proportions, okay? Which is what they're doing there. All right, next class, we'll do a lab, an angle launch lab, and more practice, all right?